To the third presentation. The presenter is Lucien Werner, who is a PhD candidate and Resnick Fellow at Caltech in the Computing and Mathematics Science Department. His research interests are in the electricity market mechanism design and power system scheduling under high penetration of renewable generation. Prior to Caltech, Lucien studied political science and math at Harvard and Northwestern universities. Lucien, the floor is yours. Please share your screen and start the presentation.
Thanks very much, Yashar. Let me share my screen. All right, so pleasure to be with all of you today. I'm going to share some recent work we've done on mechanism design for flexibility in electricity markets. Start with a brief overview of at least US electricity markets, and I think some principles are shared with European and Australian electricity markets as well. So in the top, we have some principles of the market itself. First among these is an auction style market where participants submit bids and a system operator returns a dispatch. Key to this auction is that the generators are dispatchable. That is, they submit their operating limitations and their cost functions, and then they're expected to be able to produce at any operating point in their production region. Another principle is that the demand side of the market is not dispatchable and is treated by system operators as sort of an exogenous input that's forecast more or less. The principles of economic dispatch follow this idea of merit order, where roughly lowest cost generators are committed first, and then higher cost generators might not run. And finally, as sort of coupled with this idea of the merit order dispatch is the uniform price. That is, all market participants at the same geographical location face the same price. And this price is anchored to the marginal operating cost of the marginal unit. Now, on the right-hand side, the market itself is coupled intimately with the underlying power system. And in particular, the laws of power flow need to hold for the dispatch that the market produces. And different generators have different physical capabilities, ramping limits, operating limits, and those are all reflected somehow in the price and the dispatch from the market. On the other side, the generators have incentives of their own. They are trying to maximize their profit in this auction market and might exhibit strategic behavior in terms of misreporting bids to maximize their profit. So with those principles in mind, here's a sketch of how real-time electricity markets work at a high level. So it's what I'm calling a single-shot auction. And every 5 minutes, generators submit their bids, which are the physical constraints and costs. That bid is represented by this collection of symbols here with the down arrow. Demand or load reports its projected consumption. Now, that's a little bit of a, in reality, it's more forecast than reported, but there's at least a mechanism for demand to report its projected consumption. And the system operator solves an optimization problem, computes a optimal dispatch and a uniform clearing price pi. The generators are paid pi, and the demand pays pi for their consumption. That was relatively straightforward. Under this auction design, we have a few properties. First is that we're guaranteed the minimum cost mix of generation to meet given demand. You have incentive alignment for generators, more or less. That is, they're incentivized to produce the amount that the system operator specifies. And importantly, this dispatch and price combination are revenue adequate for the system operator, and that the demand pays at least as much as is paid out to generators. However, it's sort of recognized more and more now that the demand side doesn't have mechanisms or incentives to report its preferences about how much it can consume. As consumers, we're obviously shielded in large part from the variability in electricity prices, and therefore have no way to report what our elasticity is. For the sake of the rest of the talk, I'm going to present the optimization-based formulation of economic dispatch, which I sketched at a high level on the previous slide. So the optimization problem the system operator is solving is given here, where they seek to minimize the production cost given by these CI functions, subject to power balance. And here the D sub j, T are just parameters of optimization. And the script PI set is some production set that work for each generator, let's say upper and lower bounds, for example. Now, I stress that this is a simplification, probably the simplest version of economic dispatch that there is. I'm leaving out a lot of important, I wouldn't even call it detail, a lot of important features like unit commitment, like network congestion. But for the sake of the exposition and the clarity, I'm going to ignore those for the moment. So the P star in each time period is the optimal decision that's returned by the system operator. So the generator I takes profit pi star, which is the optimal dual Lagrange multiplier for the power balance constraint, times the primal solution minus their cost of production. And that's guaranteed to be non-negative. The load pays whatever it consumes times optimal price. And as I said, this dispatch is revenue adequate for the operator. And this last property gets to the idea of incentives. So if we assume that the generators just take the price, they don't believe that they have an influence on the formation of pi star, then the optimal solution is incentive compatible. And what that means is the following. What I put up on the lower right-hand side here is the individual profit maximization problem of generator I. What they're seeking to do facing a price pi star is find their optimal production quantity, PIT, and they have to, of course, satisfy their own private constraints. So it turns out that the solution returned by the dispatch returned by the operator, P star, is exactly the optimal solution of that private optimization problem. That's a really powerful property under this price-taking assumption that we'll seek to preserve. I mentioned on the first slide this idea of merit order dispatch, and this figure sort of illustrates what that means in a graphical way. We can basically solve the economic dispatch optimization problem by picture in the following way. I'm sure many of you are familiar with this idea, but for those that aren't, I'll just briefly go through it. So we form an aggregate supply curve based on the marginal cost. So the cheapest, the lowest marginal cost resources like renewables are dispatched first on the left, and then we just sort of stack everything up in terms of, in order of increasing cost. So from basic economics, we form an aggregate demand curve and look at the intersection of these two curves to find the equilibrium point of the market. Now, because demand can't report its preferences, these aggregate demand curves are basically vertical lines, these blue lines here. So I've shown two examples at 90 and 150, and that intersection with the aggregate supply curve gives us the optimal price pi t. So the important point to note here is that if we can imagine the aggregate supply curve, this merit order curve, shifting to the right, that's going to have an impact of lowering the price. Is more lower cost generation can meet the same demand. All right, so the story on the previous slide is sort of what the power system looks like today. If we consider the future where we're under higher penetrations of renewables, things change a little bit. So here's some key characteristics as they relate to the market problem for renewables. One is that they have approximately zero marginal cost, that it's free to dispatch in the short run, more renewable energy. However, they're variable, unpredictable, and non-dispatchable. In addition, there's a low capacity factor. So per year, they're only 20 or 30% of their maximum energy is actually produced, but they produce a high peak power. And so this generation profile introduces some interesting complications. That said, in most markets now, at least in the US, the fastest growing generation type by far, and already in the California ISO market, CAISO, represents a good chunk of the installed capacity. But because of this low capacity factor, high peak power profile, curtailment happens. And this is sort of on the right-hand side. I've scaled up an actual demand curve from last year around this time, and I scaled it up by 2 times the amount of renewable energy that was available on that day. And we can see that while it's not enough to meet demand most times during the middle of the day, there's this period of time where there's an excess of renewable to meet the given demand, and this needs to be curtailed. So even though we're not quite at the story shown in this figure on the right, on the bottom, this is the actual curtailment in the last couple of years in CAISO, which is happening due to network constraints and other constrained congestion that's causing curtailment at certain nodes, sometimes quite significantly. So the idea that we'll pursue in this paper, having set up all that background, is incentivizing flexible load to basically follow the supply. And this gets at the non-dispatchable nature of renewable energy. We basically need to have demand be dispatchable in order to absorb this free low carbon energy that's would otherwise be curtailed. All right, so I mentioned this idea of demand flexibility. Turns out there's quite a broad taxonomy of what flexibility is, and sort of depends on what we want to use it for. There's a useful characterization out of the Lawrence Berkeley lab that categorizes flexibility based on the characteristic time scale. I won't go into all the details of what each of these is used for. I'm going to focus on shift flexibility, which is the characteristic time scale of days to hours. So that corresponds to the day-ahead and real-time markets, roughly. And it's the biggest opportunity in terms of allowing us to dispatch more renewable generation due to this ability to shift generation and load within like a 24-hour time scale. So definition, the shift flexibility allows demand to be shifted throughout a time horizon as long as the total energy consumed over that time horizon remains the same. So if I consume my megawatt hour at 8 a.m. versus 8 p.m., it doesn't matter as long as over the 24 hours, it's the same amount consumed. Sources of shiftable load currently come from industrial customers like factories that might have energy intensive processes that can be run at various times of the day. Also, buildings, heating loads are shiftable in some sense. And in the future, EV charging is a big potential source of this. If you plug your EV in at night, you don't care when it's doing its charging as long as by morning the energy in the battery has been filled. All right, so to dispatch flexibility, we're going to modify that basic version of the economic dispatch problem and in some key ways. So our cost function is the same. We're minimizing production costs, but now we see that the demand, D sub j, where j is the index of each of these loads, is optimized. And we're now optimizing over a time horizon. And this captures the idea that we're going to need to shift demand between times. Nonetheless, we need power balance to hold in each time period. And the constraint here, the sum of the demand over the time horizon is equal to this E sub j, where E sub j is the total amount of energy requested by each load. That is a constraint that needs to hold. In addition, we have some private constraints on the generators and loads. Now, the script D sub j set is what really represents the flexibility of the of the load. So if D sub j is just a singleton, is a single trajectory, that corresponds to the baseline case where there's no flexibility, and that's just nominal consumption of the demand. If we relax the upper and lower bounds, as shown on the right here, so the D underbar and D overbar are not the same, then the load is allowing it to be, there's some flexibility that can be dispatched. Okay, so this formulation has some good news because for the reason I just described, in the general case, this problem is a relaxation of the original economic dispatch problem I showed, which is going to result in a lower optimal cost. That means, in terms of the power system, more renewable generation dispatched, which is less carbon intensive. However, there are some surprising incentive misalignments that arise from this on the demand side. And I'm going to talk through this figure here and describe what it's representing. So this figure is the demand on the vertical axis. We have the demand utility. That's just the negative of the payment in this case. It could be something else, but for this example, it's just the negative of what the load or the demand is paying. And on the right-hand side, on the horizontal axis, we have flexibility, which is parameterized by alpha. You can imagine alpha is just like scaling the width of these upper and lower bounds on the demand. So as alpha goes from 0 to 1, 0 is no flexibility at all, 1 is sort of maximal flexibility in some sense. And this is a power system with a single load, a single generator, and 2 time periods. You see what happens is that when flexibility is not dispatched at all, so alpha is equal to 0, we have a payment of 6. And as we dispatch flexibility, as we allow the load to redistribute through time, the utility, or the negative of the payment, increases, so that the load is paying less. However, at some critical threshold value, in this example, alpha equals 1/2, the demand utility drops. That means that load is suddenly paying more, and it stays that way. So the takeaway from this is that demand can be worse off by offering its flexibility than if it didn't, in the form of paying higher prices. And the generators sort of capture this flexibility surplus, and the load gets none. And this idea of flexibility surplus is important. I mentioned in the previous slide that because we have a relaxed problem, we're going to get some lower optimal cost, and so that benefit goes somewhere, and in particular to the generators. This is not desirable because the demand we want to incentivize them to offer this service to the grid. It has positive social benefits, but if we don't carefully design how much flexibility is dispatched, it could end up being irrational for demand to offer this. All right, so that we propose in this paper a mechanism to address this incentive issue so that demand is incentivized to offer flexibility. We do so in the following way. The top part of this optimization problem is what we saw in the previous slide. We're going to add 3 sets of constraints to this optimization problem, and I'll briefly describe what they're doing. So the script T set is the intervals for which there's an excess of renewable energy over the baseline consumption, shown in blue. And so for all the time intervals within this script T set, we're going to upper bound the demand consumption by the maximum allowable renewable. So we're not going to allow any conventional generation to be used during the script T time set. And then the last 2 sets of constraints, basically, we only allow the demand to flex up in script T, and we force it to flex down every other time. These are important to have these sort of complementary directions on these inequalities, because with shift flexibility, the total amount of energy used over the whole time horizon has to be invariant. So if I flex up in one period, there has to be a corresponding flex down in some other time period. All right, so I'm going to review the cartoon from one of the first slides now we consider a multi-interval auction with flexible dispatch of demand. The high-level structure is the same. So generators submit their bids, which haven't changed, except now they're doing so for the entire time horizon. The loads submit their bids, and the load bid shown on the right here is upper and lower bounds, so that's their flexibility in each time period, and then a nominal baseline consumption that lies somewhere between those upper and lower bounds. The operator computes the optimization problem that I just described and computes the optimal prices. Now, the energy price stays the same. That's still the Lagrange multiplier for the power balance, and the revenue that the generator I gets is now the price trajectory or price vector times their production minus their cost. The loads, on the other hand, they pay the baseline price for the energy, and those that offer flexibility get paid this flexibility price kappa, which I'll discuss next. And this flexibility price kappa is applied to their deviation from the baseline. So that's shown here. So the payment that the load makes is the negative of this, and then they get paid negative of their energy consumption at the original price, and they're paid if they deviate from their baseline. Now, if they don't deviate from their baseline, this flexibility payment is zero, and they're just paying what they would have originally. So compared to the baseline case, which I keep referring to, which is when all the loads consume D0, if there is non-trivial flexibility, if there's some gap between these upper and lower bounds on the demand flexibility, then we get the following properties. Lower generation cost, the demand that offers flexibility pays less because this kappa times the deviation is non-zero. The demand pays the same as they would have under the baseline if they don't offer flexibility. And importantly, which I'll discuss later, profits for generators decrease. So generally what happens when we dispatch flexibility is that this price pi decreases, and that means lower profits for generators. So I mentioned this flexibility price kappa, and then the design of this price is important so that we have some desirable properties. So kappa sub t, or kappa is the vector of all kappa sub t's, is a time-varying flexibility price that's paid to the loads that offer flexibility. And here's some properties that kappa needs to satisfy, or that we'd like to satisfy. One is that the price is uniform, so all loads are paid the same price for the same amount of deviation. The sign of kappa needs to correspond to the direction of dispatch flexibility. So if I dispatch up 1 megawatt during a period, then the kappa needs to be positive. If I deviate down from my baseline, the kappa needs to be negative. This is important because both up and down flexibility are necessary in order to redispatch, and we want there to be positive incentive to dispatch in both directions. Finally, the sum of all the flexibility payments needs to be equal to the flexibility surplus, and this flexibility surplus is this S defined as such. It's basically the difference in revenue in the market between the baseline case, so that's pi 0, and the flex case, which is pi sub t. And this is sort of roughly the change in demand side welfare, and we want that change in demand side welfare to be redistributed in the form of flexibility payments. So any price kappa that satisfies these properties, we have our provable properties, which I'll get to in just one second. For example, what we do in our work, we can propose this optimization-based formulation. Now, this is not the only one. We also discuss a couple others designs for kappa, but here's one that satisfies these three properties. So we enforce the sign constraints. That's the second bullet point. We put the sum of flexibility payments, which is on the right-hand side, just force it to be equal to the flexibility surplus, has a constraint. And then this objective function promotes some smoothness or reflects some time varying value of the flexibility. So when the flexibility is higher value, kappa is larger. When flexibility is less value, kappa is smaller, or the magnitude is. All right, so under these properties, we get the following provable result. Basically, loads are better off offering flexibility than consuming their baseline. This is the property and mechanism design of individual rationality, that by participating in the market mechanism, loads will be at least weakly better off. The second is that the dispatch retains its incentive compatibility on the generation side. And this is important because if we introduce some mechanism on the demand side, we don't want to disrupt the desirable incentive following properties for the generators. I will note the subtle point that the generators are worse off under the flexible dispatch, but they still have an incentive to follow the system operator's instruction. Finally, the settlement. So that's the combination of the flexibility price and the energy price, and the allocation of demand and production are revenue neutral for the system operator. All right, so to illustrate this a little bit, make it concrete, I will quickly review a case study that we did on the CAISO market. So on the left-hand side is a baseline dispatch of the market, where the dotted line is the consumption on a day from last year, and the generation is represented by these different generation types. And everything is from the actual data, except that I've scaled up these renewables roughly by 2 times so that we get a curtailment in the middle of the day. And finally, I've represented with this gray region the aggregate flexibility of all the loads in our market, and they're simulated a demand side of the market that doesn't currently exist. All right, so on the right-hand side, this is what happens when we do the dispatch the demand flexibility. And the red curve is sort of the aggregate demand when we allow the loads to be flexible. We see that in the middle of the day, when there's this excess of renewable, we're able to increase demand to take advantage of that. And correspondingly, during other times of the day, when there is not an excess of renewable, we dispatch down. And this is where the sort of the cost saving and the lessening of the carbon intensity of the generation mix comes, because we're consuming less of the thermal generation, conventional generation during these off-peak times. Briefly talk about the demand side simulation. So basically proportionally disaggregated the net load to get these baseline trajectories shown in black. This is a particular load profile shown here. Then we generate these flexible demand trajectories around the baseline. These upper and lower bounds are arbitrary, as sort of shown here. I randomly generated them, and so they can roughly be anything. But when we do the dispatch, the red, which is the flexible dispatch, has to be between these upper and lower bounds. So the area under the red curve and the black curve are the same. That's the total energy that's consumed. However, by offering this flexibility, the load sees in this simulation nearly a 50% cost reduction for redispatching only 7% of its energy. So there's a big incentive for loads to do this under the right mechanism design. Finally, present the prices from the simulation. So on the top, we have our energy prices. And as I mentioned, under the flexible dispatch, the pi tilde here, the red curve, is the new energy price, and it's a lower bound on the baseline energy price. And this is what causes the generation revenue to decrease. In the second plot, we have the flexibility price, and we can see it sort of mirrors the availability of excess renewable generation. So in the middle of the day, we have our kappa that's above 0, and that's incentivizing upwards flexibility in demand. In the beginning and end of the day, we have our kappa that's less than 0, which is incentivizing demand to flex down. And so both of these directions are necessary in order to be able to shift demand in time. All right, so this table here is sort of summarizes the welfare transfers that happen between the generation and demand sides of the market. A lot of numbers going on here. So I want to draw your attention to the ones shown in red, which is sort of transfer that between the generation side and the demand side. So while the generators as a group lose out in this flexible dispatch setting, they have a negative change in their revenue, the demand increases its welfare. And the increase in demand welfare through our flexibility price cap and our allocation mechanism is being redistributed to those loads that are offering this flexibility service to begin with. So while generators lose out, we see this as sort of being the right thing to do to incentivize a service that we want, which is flexibility from the demand side of the market.
Lucien, sorry, if you can wrap up quickly.
Yes.
Okay, perfect.
Yes, anticipated my last slide. So a few things that I haven't talked about are strategic behavior from demand and the fairness of the allocations between the demand and generation side. And finally, incorporating this demand side mechanism with more realistic components of the electricity markets like unit commitment, ramping constraints, and line congestion. These are all part of our ongoing work. Anyway, thanks very much. I hope I haven't run over too much, and I hope to hear some questions if you have.
Thank you very much, Lucien. It was actually a very, very interesting talk and very clear. I see that it says several people are typing, so you see that there are a lot of questions. I also have a lot of questions, but unfortunately, we should take all the questions offline. So we'll post all the questions and you follow up on that, but it's a very interesting talk. Thank you again, Lucien. So